So in this video, we're going to talk about our fastest reacting carboxylic acid derivatives, the acyl chlorides, sometimes called acid chlorides. An acid chloride will react with a nucleophile like water to form a carboxylic acid, or an alcohol to form an ester, or some kind of an amine or even ammonia to make an amide. In all of these cases, again, the reactivity of these acyl chlorides is the fastest, right? Because the chloride anion, so the halide ion that leaves, is going to be a weaker base than the incoming nucleophile. So these are our fastest. Carboxylic acid derivative to undergo nucleophilic acyl substitution. So in other cases, say with an ester or an amide or a carboxylic acid, you're going to find yourself needing to use some kind of a catalyst to get these reactions to sort of go, right? But not with an acid chloride, because the leaving group is the chloride ion, which isn't even basic at all. It's pretty much neutral, right? So it's a great leaving group. You can take your acyl chloride. So remember, we have the acyl group here. That's your acyl group. There's the chloride. That's going to be your leaving group. We could have some nucleophile come in and attack. So we'll just pick some generic, say, alcohol. So it's a neutral molecule, right? Not the greatest nucleophile, but it's nucleophilic all the same. It has a lone pair of electrons, right? So it's a weak nucleophile. Water and alcohols are weak nucleophiles, right? Again, remember, the more basic it is, the more nucleophilic it can be. And this is going to be in equilibrium with what we call a tetrahedral intermediate. So we put the electron density up onto the oxygen. It's negatively charged. We have taken an sp2 hybridized carbon, and just for a moment, we've turned it into an sp3 hybridized carbon. This little prime on the R just means that it's a different R than the other one. They can be the same, or they can be different. In this case, another equivalent of the nucleophile, because usually if you're using alcohol or water, usually, because these are all reversible steps, and at equilibrium, right, if you have an equal chance of forming, two different products, and one of them is going to be your starting material, in order to encourage the reaction to go to the right, by Le Chatelier's principle, we can put some extra reactant in the pot. So usually if it's like an alcohol or water, that's your nucleophile, we go ahead and just use it as the solvent so that we have an excess of it around. And so we can use that to deprotonate our intermediate. What you'll get is this tetrahedral intermediate. These are unstable, and with a good leaving group sitting there, we reform that pi bond. So the tetrahedral intermediate, in other words, is going to collapse. When we do that, you can either get rid of the halide ion, so Cl minus, or you can get rid of the alkoxide ion. That would be R prime O minus. Well, chloride is going to be a weaker base, much weaker base. And so that's going to leave. And this last step I'm drawing as irreversible. Chloride is essentially neutral. It is not going to be basic enough to come back in and attack the carbonyl. And in this case, what we got is an ester. So your nucleophile is going to attack your nucleophile, in this case the alcohol, possibly used as the solvent, is going to come in and it's going to deprotonate that oxygen, deliver electron density back to that oxygen. Your tetrahedral intermediate is going to collapse. The weaker base is going to leave, and that's going to be the halide ion. And in this case, the ester is going to form. What reactions do we see with acyl chlorides? Well, for nucleophilic acyl substitution reactions, typically we'll see formation of carboxylic acid. So I could take like an acyl chloride. I could use water as my nucleophile, usually in excess. What do I get? The carboxylic acid. Plus hydrogen chloride. So one way that you can view this is you could highlight your leaving group, and one of the hydrogens on the water molecule, you see your HCl comes from there, and the OH comes from the rest of the water molecule. I could take an acyl chloride and I could allow it to react with an alcohol like we just did. Pick a different one this time. Trying to draw the structures just a little bit differently so you can see how they might be presented to you, say on an exam or a homework problem. You're going to react this acid chloride or this acyl chloride with an alcohol. You will get an ester. It's important to note that the oxygen that is now attached over here came from the alcohol. We'll see this again when we react carboxylic acids with alcohols and make esters. And hydrogen chloride. So again, following this along. We can also react an acid chloride or an acyl chloride. So I'll draw something a little different here. With two equivalents of an amine. So you're going to need two equivalents of amine, and this is kind of going to be a big deal, because essentially one of them is going to end up getting protonated. And so you're going to need one there to act as your nucleophile. And in all these other reactions, we're making HCl. You make HCl, you protonate the amine, you no longer have a nucleophile. So we use an excess, or at least two stoichiometric equivalents of the amine. And we will get an amide plus the ammonium salt of the amine. So this is the protonated equivalent. So here we have our carboxylic acid. Here we have an ester. This is an amide. And this is an ammonium salt. That is methyl ammonium chloride. Again, our acid chlorides or our acyl chlorides are our fastest to react of all of our carboxylic acid derivatives. They're faster than esters and carboxylic acids. Esters and carboxylic acids are kind of like the same, right? And how do we base this? I mean, it really depends on the molecule, the rest of the structure of the molecule you're dealing with. But if you're just taking a garden variety, if everything had just a methyl group on the other side, and we're just comparing the leaving propensity of the leaving group, we can judge that by how basic it is, right? Hydroxide and alkoxides have pretty similar levels of basicity. So the pKa's of their conjugate acids are relatively close, right? The pKa of water is 15.7, and the pKa of an alcohol, depending on the alcohol, is somewhere between like 15 and 16, or like 15 and 17, or something like that. So they're pretty close, right? So esters and carboxylic acids react similarly. Acyl chlorides are going to react the fastest because the chloride anion is the weakest of all of the possible bases that could be our leaving group. And then amides are going to be our slowest to react. So the amide anion, NH2, is too basic to leave by itself. So we have to protonate that to get ammonia to take off. And we're going to do reactions with all of these separately in separate videos. But again, reactions of acyl chlorides are first carboxylic acid derivative moving in the direction of fastest to slowest reactivity.